All right, so good afternoon, everybody. And today we're going to be writing a binary tree. So the only files that I've set up so far are a simplistic and empty main file that includes the binary tree header with its header guards, and a bit of a weird include on the bottom here. So as it says in the comment, this include will allow us to use templates that we can define in a separate file. So normally we talk about templates have to be defined in the HPP file. That's actually wrong. Generally, templates in actual C++ are defined in a header file, or sorry, declared in a header file, like normal. But then you go over to a .tpp file and define the templates. That's a template implementation file. But that is not recognized by VS Code. So I went with .cc, which is another C++ file extension. So I will use .cpp for main files that are intended to be standalone compiled, and I will use .cc files for kind of code that is not intended to be standalone compiled. Because of this include, we will only need to include binarytree.hpp, and whenever we compile, we don't need to list binarytree.cc in the compile list. What include does is it basically copy and pastes the file. So it's as if we have written the definitions for binary tree immediately after their declarations, which we're doing at the top of this file here. Okay, that was a bit of background on how a templated object can be split between multiple files. Let's get into writing it now. And a quick aside before we start writing is that writing a data structure, particularly something like a binary tree or even something that's more complicated, can be very difficult. So what you want to do is you want to get yourself comfortable, find a nice seat, find a nice location, kick some music on if that relaxes you, and get programming. But anyway, you're here to learn how to program a binary tree, so let's do that. So the very first thing that we'll want is to declare our class binary tree. We could try and do some kind of an n-ary tree, which is a more generalized form, but let's focus on a binary tree for now because this is going to be a little simpler. So binary tree, of course, means two-direction split tree. So if I pull out a whiteboard, we can take a look at what a binary tree looks like, which I find it's a little bit useful to draw these things before we actually code them. So what we have at the very, very top is what's called a node. So that's this little circle. And you can think of it a little bit like the node in a linked list. So the one at the very, very top, you can think of a little like the header of the list, but it's called the root in the case of trees. We use a lot of kind of tree and leaf-like words whenever we describe trees. So anyway, we have the root. Following from the root, we have nodes, one left, called the left child, and one right, called the right child. And the binary tree only has left and right. A trinary tree, which has a branching factor of 3, meaning you have a left, middle, and a right child. They also have quaternary trees, which is a factor 4. And you have technically n-ary trees, which are a factor n, meaning that every time you go down, you split to n different little subtrees. And they are subtrees, because if we were to consider the node that I am currently drawing children of, this one here, to be a root, this is itself a subtree. It is a tree to its own. So binary trees don't have to be balanced or anything. So what we could do if we wanted to is we could have children arranged in exactly this array. So on the left branch, we have a depth of 3. We go down to 3. Sometimes you would say depth of 2 because you count the arrows. It kind of depends on your formalism. I prefer to try and count nodes, which of course means that I basically say depth of the root is 1. I think whenever I was taught, though, they told me that the depth of the root was 0, and therefore the depth of this node is effectively 2, because we would go 0 to 1, 1 to 2, in which case you are effectively counting the arrows. So again, you have to kind of decide how you might consider that, but depth is an important property we can measure, and we can count depth here as well. So again, let's assume actually that the root is depth 0. So that would mean depth 1, 2, 3, which means the height of the tree, the height is always counting from 1. The height of the tree is 4, because the height is equivalent to basically the maximum depth plus 1, because depth starts counting from 0. If you start depth counting from 1, then the height is just equal to the maximum depth. So, because height is a property of the entire tree, depth is a property of a particular node within a tree. So in other words, each node has its own depth, but the tree has one entire height. Okay, cool. So that is some of the base descriptions that we need. So we know now trees start with a root, and then they have a left and a right, and each node will have its own lefts and rights. So a little bit like a linked list, we can't immediately get at whatever node we want, but we start at the header or the root, and then we'll follow whatever path we need to get to where it is that we want to go. Now, a little bit unlike a list is that this is no longer linear, right? We have a option to go left or to go right at every single stage. We can make these decisions. Similarly to a linked list, what we can do is we can add in some extra dummy elements at the bottom that function a little bit like trailers that will be used as a you're done iterating here. I prefer not to do this implementation whenever I end up writing code, because I have a ton of dummy nodes. So instead, I prefer to leave them as null. So by not writing them here, I want you to assume that the children are null. So the left child of this node is null, the right child of this node is null, and both children of these nodes are null. Okay? And then the last bit of terminology that we want to discuss are the leaves. So a leaf is any node that has no children, which means that all of these are leaves. They're basically their external nodes. And, you know, that means that in the case of certain trees, we can state certain things about the leaves. We'll talk about binary search trees at some point. And binary search trees, you can determine a fair bit about the leaves. Heaps, the leaves, depending on if it's a min heap or max heap, the leaves will either be the biggest or smallest elements in your heap. And a heap is a form of a tree. So is binary search tree. It's in the name in that case, so it should be a little obvious. But anyway, what we're going to do right now is we're just going to write a very simplistic tree, and then we're going to use the concept of polymorphism to extend our simplistic tree into a heap and to extend it into a binary search tree. Word of warning, heaps and binary search trees are different things. But anyway, that's kind of our simplistic concept, so let's go back to the code. So we've created our class, and because we're going to be focused on extending this, let's try and make a lot of the data, instead of being private, protected. So, bit of a refresher for those that may have forgotten. Protected means that any data that you have that is protected, or any functions that you have that are protected, belong to the descendants of the class, and they can be accessed by that class's descendants. So effectively, this means that the heap and the binary search tree will also have these values. Okay, cool. So what we could do is we could try and keep track of the height of the tree, its number of elements, and its root. Or minimally, we could just keep track of the root and calculate the height or the number of elements manually every single time. It all depends on what it is that we're going to do. If we're going to be asking how many elements are in the tree quite often, then we want that to be something that we store in memory and that we can just return. But if we rarely ask for how tall the tree is, then, or how many elements it has, then we can write it as an O of n function. I think in our case, we'll write it as a constant that we keep track of. at least the number of elements. The height we can allow to be calculated in O of n time. This way we get to see a bit of both. Okay, so again, we're going to use the size type. Remember, a size type is an unsigned long, but in order to get that, we will need to include C standard lib. You can also include Ostream or many of the other libraries, and they'll give you access to the size type, but it is an unsigned long, at least on a Linux system, and this is a WSL Ubuntu, therefore, for all intents and purposes, it is a Linux system. We will change out this import, by the way, to be Ostream in a minute, but for now, we just put the minimal one that we need. So anyway, we want to keep track of the number of elements. So what we can do is call this len. This way I can have a function called length and or a function called size, and they can access len. Okay, cool. So then what we can do is we can store the root. But in order to have the root, we need to have a struct, which is going to be our binary tree node. So a little bit like our linked list node. So anyway, what let's do is we'll say struct node. Right? So this defines our type of our node here. And I'll put it at the top. What we want to do is we'll want to go out here and we'll want to say class binary tree, struct binary tree node, like so. And I believe that this is a correct syntax. I'm a little concerned that the colons are red, but that should probably be okay. So then what we can do is we can say, let's create a node of type, not of type, but of name root, right? So this will be our root. So what information goes into the nodes? Incomplete type is not allowed. Tell you what, let's try and write it in line. That'll probably make it a little happier. I just tried to write it out of line because I didn't want to have to deal with this taking up a lot of space inside the class, but it is what it is. So a little bit like before with our linked list, we want to store the object, which for now, let's write an int one. So we'll say int object, and we want to store, instead of a next and previous pointer, a left child and a right child. So what we can do is we can say a node pointer left and another one called right. Remember, whenever you list multiple pointers, you have to put the star in front of each of them. If you forget to put the star, it will become an actual node object, because if we format this document, you can see that the star jumps onto the variable name. It's not part of node, it's part of the variable name. So that is the intuition. But okay, so we have our node now, and we have our root. Let's try and write some simplistic node constructors. So what we can do is we can say node, which takes in an int object, which we can say is initially 0. And then a node pointer L, which is of course going to be left, but that'll be null pointer by default. And we'll take in another node pointer R, which will also be null pointer by default. And then we can use the list initializer. We can say something like object is constructed from object. Remember that you can use curly brace or parentheses construction in this list. And if the variable names are the same, that is A-okay. But anyway, then left will construct from L, and right will construct from R. And then we can just put our class curly braces. Now, I do want to change one thing about the design. Whenever we construct this, these variable names are exposed publicly. What do I mean? Well, if I was trying to construct root with values, we have our constructor here, and I can see obj, which is the object, but then I see L and R. And if I don't immediately know what that is, I could get confused. So what I will do is I will rename these to left and right. In fact, I'll be even more clear and call it left child and right child. And for the object itself, we'll call it object. So now we have to go over here and make it a little bit more clear. So we can go and just move that in there. But the reason that we did this, remember, is just that these variable names will be seen later on in the program. Now if we take a look, object, left child, and right child. I tend to be in favor of being a little more descriptive whenever somebody else could see my variable names. In the case of something like obj, which they will see, I'm fine with being a little less descriptive. But, or len, right? But for something where they will see it, I want to be as clear as possible to help them out. So anyway, we store the root here. And this is often stored as a pointer, which is a little unlike what we may have seen if we'd done linked lists before. You might have done a full header object. But if we think about it, instead of root being a full object, if root is a pointer, let me grab it and move it away. That means that root is actually a memory address. So I'll draw that as a little dot, which will then go over and point at the first node. And then we have a really easy check for is empty, which is just if root is null, then the tree is empty. But anyway, let's go talk about writing some of the functions that this tree is going to need. So a binary tree should be able to tell you the following things. It should be able to tell you whether or not it is empty. It should be able to tell you its size. It should also be able to tell you its length, interestingly, which is the same thing as size. And the reason that we do both is because standard objects in C++, like vector, will do both. So we want to try and emulate as much of what C++ does as possible with our code, because this way it will be as familiar as possible to fellow C++ programmers. But anyway, so now we have done size and length and empty. So what we want to do is we want to consider what other things we might wish to do to our tree. Well, it might be nice to print the tree. So in order to do that, we need to add that as a friend function. So we'll say friend standard Ostream. But now that I've required Ostream, I can't just use C standard lib anymore. I need to bring in iostream, which will actually likely bring in C standard lib for me. And now I have Ostream, but I still have size type. So anyway, now what we can do is we can write our operator, bit shift left, and we can put in the Ostream by reference and call it OS for Ostream. Now this is confusing to you and you think of this as meaning OS is an operating system, just call it O. I've seen that done as well. And then what we'll do is we will need to pass in a const binary tree by reference, and we'll call it BT. Okay? And there we go. Remember, we put const on the end of the function if it won't change, but in the case of friend functions, we make the object itself const if the object won't change. Let's discuss some of the other things that we may want to do with a binary tree. So we may want to try and index into a binary tree, but this is actually a bad idea because binary trees don't have a linear index, so it doesn't make a lot of sense to do, and binary tree accesses happen a lot like how they do for a list, where we need to start somewhere and then search our way down. So a standard indexing system is probably not a good idea. However, what we can do is we can write a search function. So what we can do is we can write a search function that will return a reference to a node. So we'll say const node reference search int data const. Because it's returning a const reference, it can't change the tree, so we can make it const. Let's also write a search that doesn't return const, but returns something that is actually changeable. You'll notice this is a lot like our operator brackets from whenever we did a dynamic array such a long time ago. But now we can kind of search through some data within the tree, which is very nice. Another thing that we might want to do is we might want to add the ability to insert something into the tree. So what we can do is we can write a function called insert, which will take in a node reference, we'll call it n, and it will take in an int, which we'll call object. and it will perform the insert operation. Now, insert doesn't return anything, as say, so we'll return void. What we could do, for efficiency's sake, is we could return a reference to the newly created node that is going to be inside of our tree and contains object. It's probably not necessary for us to do that, but let's do it anyway. So node pointer insert. Problem is, though, where do we want to insert? So let's make this one insert left, and we'll make the other one insert right. So now we have two different ways to insert. We insert left of n, and we insert right of n. Okay. Now, does n need to be a modifiable node, or can it be a const node? I think it can be const. That's actually false. N has to be modifiable. And if we think about why, what we're going to need to do is we're going to need to set n's child pointer, which is why n must be modifiable. Some implementations of tree, by the way, have a third pointer here, which is to say a parent pointer. So instead of just pointing downwards, you also point upwards. You'll notice this is a little bit like a doubly linked list. In that sense, we are not going to be implementing parent pointers because they are an additional bit of complexity that is helpful. You can use them to reduce some complexity later on, but it isn't strictly speaking necessary. And the reason is that trees are actually a very recursive structure, which means that we are going to be able to do a lot of things with them recursively, and it will not make sense for us to need to follow parent pointers when we can simply pop the stack and return from that. Okay, so now we have the ability to insert, and we could also write the ability to remove. So we can say, well, remove would remove a node of the object. So we'll write a few different removes. We'll write a void remove, which will remove the object from the tree. And then we can also write a remove left, which will remove the left child of a node. And what we can do is we can have it return the data that is in that child. And we can write a remove right, which will do something very similar, but of course to the right child instead. So we now have the ability to search for data, which will give us a node back. We have the ability to insert to the left and to the right of a node. We have the ability to remove data from our tree and to remove left and to remove right. And let's also write something called traversal. So I'm going to write basically 3 different traversal functions. But it turns out there is actually a better way, which we will also write. So the first traversal function will be called a pre-order traversal. And it turns out that a pre-order traversal, if we were to properly write this, would involve lambdas, which now that I think about it, isn't something that many of you have seen. The idea being that a pre-order traversal will perform an action on every node in the tree in a particular order as we are stepping around the tree. And because you all haven't seen lambdas, which are basically one-line functions as variables that we can pass, let's not write any of the traversal functions now that I think about it. We will write some traversals, in the form of an in-order traversal for our print, but we will not write anything like anything too crazy, anything like a lambda. So, okay. Well, this is a nice simple set of functions, and I think we could probably use this to do some really good things. So we can go over and start writing these functions. So what I'll do is I will kind of move this to the side. And let's actually minimize that terminal. We don't need that right now. So here we are in the template implementation file. Again, TPP is the general extension for this, but because VS Code doesn't recognize it, we're going with .cc, which is just a C++ file. Okay. So what we want to do is we want to include the binary tree.hpp and then just ensure that that compiles, right? Because if this didn't compile, that would mean that we have a multiple definition error. So what we'll do is we'll briefly pull up that terminal. And what we need to do is we need to cd into this location. So we'll cd into 221. And particularly, we are looking at section 5, which is trees. Within that, section 1, which is binary trees. Okay? And if we ls, we should be able to see that our code is here. So what we'll wish to do now is we will wish to compile. So let's type our make program. And it looks like make worked successfully, right? It ran our compile, like we expect. And we didn't have anything strange. In fact, we got a green, which means that the make worked. We can actually check that that worked by typing echo $? You can see 0. That is a successful return. If you return anything other than 0, it means not successful, which is why main, back in 121, you would always be told to return 0. But okay, so now we've included the header file, and we can start to reference stuff. So now we can say, let's write binary tree, where we want to write the empty function. Notice we haven't done any constructors yet. The reason for that is that we probably want to go with a default constructor, and we are going to need to write our own special destructor as well as a copy constructor and things like that. But a constructor for a tree doesn't really make sense a lot of the time because trees grow automatically whenever you put things in them. And it doesn't make any sense to give them an initial size. It doesn't make any sense to give them anything other than maybe an initial value to put in the root. So we might consider a constructor of that form. But okay. So a binary tree here will write the empty function. And of course, this function returns bool. And all we have to do here is we just have to return whether or not the size is 0. So the reason that I have written this, calling the size function as opposed to using the len variable, is that the compiler is very intelligent, and it will actually simplify this size into the len variable whenever it compiles. But if I end up deciding to change the way size works and rewrite it a little bit, then instead of the compiler simply being dumb and using len, it'll do whatever I did for size. And this gives us a little bit more flexibility in terms of how things are written. So this way, if I change the way size works, empty will automatically change to reflect it. But for now, what we can do with size is we can just return len. And then we can discuss the length function. So the length function, you think we could also return len, but very much like empty, we want to try and be very good about our use of reusable code. So if we take a look at this, we now have written 3 functions, the size, the length, and the empty. They should all be very simple, and let's ensure that our compile works, which it does. Okay, so now that we've written those 3 simple functions, we would actually have to get thinking if we were to write the search, the inserts, the removes. So instead of doing anything like that, at this stage, what we will do is we will write our constructors. So whenever we create a constructor that only takes 1 argument, or sometimes 0 arguments, we wish to mark it as explicit. So explicit means that it will not call the constructor unless we explicitly, that means write it out ourselves, call it a constructor. So anyway, we explicitly construct a binary tree, which will take an int, which is going to be the root object. Again, it's nice to be verbose. Now, if we were to change this tree to use something other than ints, this would change. Okay, so now what we want to do is we want to say that the root is going to be a new node constructed from the root object. So whenever we do this, remember, it's not saying we assign root object. It's saying that we call the root constructor with root object. although root is a pointer. So what we actually need to say is we need to say a new node with the root object in between it like that. Now again, you all are probably used to seeing parentheses for a constructor, so let's try and do that to make your experience a little better, so it looks a little more familiar to you. So anyway, what we're doing now is we are basically constructing the root in this manner. So let's also write a few other constructors. So what we'll do is we will go over here and we'll say that we want to have a binary tree that will be able to be copied from another binary tree. And since this is a constructor, what we'll do is we will construct the root, and we'll just use the default constructor, which will construct it as a null pointer. Right? Because the default constructor for pointers is to set them to null. So anyway, that's good. We should also actually set the length while we're at it. So in this case, the length of the tree is now going to be 1. And again, we'll be consistent. We use our curly braces. In this case, the length of the tree is going to be 0. There's nothing in it. Okay. And we'd have to write this constructor, obviously. It hasn't got it written yet, so what we'll do is we'll mark this with a to-do. That means I've got to write it later. Write copy constructor. And this is a good way to program. You basically want to set yourself up with code that you can write and plan to write it later, but don't bother getting bogged down in the details. Okay, and this will be the move constructor. And then what we want to do is we want to write a virtual destructor. So this may not be something you've seen before, but the idea behind a virtual destructor is that we want the destructor to be callable by the children. So whenever the children get destructed, it'll destruct the base as well. We especially want this because we're going to have a lot of dynamic memory. So anyway, we've got a virtual destructor, and we're going to be writing that over in the CC file. Let's also write, and in the case, by the way, of a copy constructor, you don't need to worry. In the case of the operators now, because we want to do the full rule of 5, what we'll do is we'll return a binary tree reference. Let it be operator with a single equal sign, which can take in a const binary tree. And a similar thing, but it'll be move. Okay. So now that we've got all these, let's go over here and we'll copy. Go back over here and we'll paste. So whenever we end up writing the definition, we don't need the word explicit here anymore, at least as far as I recall. And we don't want to have definitions in the header file. Generally, that's something you want to avoid. So what we'll do is we'll just mark these off. And we can go over here and we can write them. So the CC file, you notice now, has got those definitions that we were working on, but in order for them to work, we need to scope them properly. So we would say binary tree. Okay. For these as well, right? Wonderful. So we're now set up to be able to write these. And we do need to actually write definitions for them. So what that error message was telling us. Okay. So we've done a lot of setup, but now we're actually ready to potentially start writing some of these, right? We already have the simple constructor. And in the case of the copy constructor and the move, we need to write those as well. So in the case of the copy constructor, what we want to do is we want to basically do a pre-order traversal where we want to try and insert those items that are in BT into ourselves. And the best way to go about doing this is, instead of actually constructing with length of 0 and root, we'll construct with length of 1, putting a root in there, and with the root that we can put in is we will just put in bt.root arrow, because remember root is a pointer. object first, and then null and null. But our root is going to be a pointer, which means that we can't construct it with an object, so we'll need to say a new node. We notice you don't put in the left and right children. This is just like whenever we try and copy a W-linked list node. We don't want to copy the memory addresses. We just want to copy the data that's in there. And then what we'll want to do is we'll want to call insert on every node that's in BT. The question is, how do we get all of these nodes? For a linked list, it was easy. We could simply do a iterate all the way through all of the pointers. But trees, if we were to iterate through the pointers, let's say we iterate down all the left children, we hit the end. Now we have to try and figure out how to pick up these right children, so it's a little bit tricky. So what we want to do is we want to write a pre-order traversal. Surprise, surprise to me that we're writing one so early, but that's okay. Now, I'm not actually a fan of writing code in the copy constructor, especially because this code's about to be recursive. So let's set up some helper functions for us. So what we'll do is we'll create a function here called copy. And what copy will do is it will take in a node reference, and it'll actually take in 2. And we can then go about inserting the nodes. So what we'll do is we'll say that we'll say it's void for now until I think of anything better for it. So copy will take in a node reference, which is called our node, and a node reference, which is called their node. And the idea behind this is that we want to pass it the root of our own tree and the root of their tree, and then we can go about performing copies. Which we already have copied the roots directly, but this way we can copy the children. Okay? So, very, very nice. So then what we can do is we can also write another function called, well, we're getting ahead of ourselves. Let's just use copy for now. So what we want to do is we want to, for our constructor, just call copy with our own root and with BT's root. And these are actually node pointers, not node references. So what we want to do, I guess, is dereference them is probably the easiest way. So this pointer is dereferenced, remember? And that means it's now an object. So what we can do is we can go over here, we can grab our copy, which you notice I put in the protected space, and we can come back over here and we can try and write it. So I like to write my protected code at the top, but you could also write it at the bottom. So wonderful. Binary tree will require to be scoped. And what we can do now is let's assume that our node is already in the tree. So then what we can do is we can call our insert left function, which we haven't written yet, on our node, and the data that we want to insert is their node's left child's object, provided that their node's left child exists. So what we can say is if their node's left child exists, do this. We can do the same thing with the right, but we want to call the insert right function. Sorry. So this now inserts the left and right nodes, but this doesn't do anything for helping us to grow out our own tree. So what we can do then is after we've inserted the left node, let's put some curly braces on our if statement here. What we want to do now is we want to call copy. So this is where the recursion comes in. So what we can say is we can say copy of our node dot left. This is of course going to be a pointer. So what we'll need to do is we will need to dereference it. And we'll do a similar thing here. So what we want to do is we want to call copy, but now it'll be on our node dot right, if you want to dereference. Now, we also want to do the same thing with theirs. So we can say their node dot left, which will dereference, and their node dot right, which will dereference. And this will let us grow out. It'll first grow a node into our tree, and then it'll go down the left branch, constantly growing nodes. And then once it hits the bottom, it'll try and grow the right branches on the way up. So effectively what'll happen is, first we grow this, then we grow this, but we can't grow anymore. So then what we do is we grow this, and we can't grow anymore. So then what we do is we go up here, and we've already grown this node. So then we go back up to the top, and we grow this. And then we grow this, but we can't grow any more on that side. So we grow this one. We can't grow any more at all. So we go back up, we go back up. We can't grow any more on this side, so we go back up, and then the tree has been fully copied. So this is the idea. And it is a bit of a copy. So what we can do now is we can just call that function with the root and bt root, and that is our copy constructor, which is very nice. Our move constructor is going to be really even easier. What we wish to do is we wish to set our length to be bt.length. We wish to set our root to be bt.root. And we wish to set bt.root to be null pointer. And bt.length to be 0. This means that we will need to write a special case for our insert function to happen whenever the tree is empty. In other words, whenever the root is null and the size is 0. So, okay, wonderful. Now what we want to do is we want to write our destructor. So the destructor is a really good example of what's called a post-order traversal, which is actually something that we just wrote. If a recursive call comes after you manipulate the object, it tends to be a post-order traversal. That we just did was a bit strange. This should be much easier. So what we want to do is we want to write a function here called destroy, which will take in a node pointer. The reason it wants to be a pointer is we are going to call delete on it, and we can call this node. So then what we want to do for our destructor is quite simple. We just want to call destroy on the root. And root is already a pointer, so we don't need to do anything fancy, and it will go about destroying the tree. So what we can do is we can go back up here, and we can write a destroy function. So remember, we'll need to put that in, like that. Wonderful. So now we can write destroy. And destroy, all it needs to do is it needs to say if node, then what you need to do is you need to call destroy on node arrow left, destroy on node arrow right. It's okay if these are null, because this will check to make sure they aren't null, so they don't do anything if they are. And then what we'll do is we'll call delete on node itself. And what this will do is this will clean up the node's memory. But if we think about what happens is because of the recursion, what we do is we end up starting out, at the root, but then we destroy the left. And then we can't destroy the, well, we try to destroy the left, but there's nothing there. So we go back up, and then we try to destroy the right, but there's nothing there. So then we call delete on the current node. So what that'll do is it'll cross out the current node. That's what that delete does right there. And then we're done with this one. So we go back up, because recursion, to this node, and we try and call destroy on the right. So we go here, and we try and destroy its right child, which doesn't exist, so that doesn't do anything. And we try and destroy its right child, which doesn't exist, so that doesn't do anything. So we go back up to this node here, and we call delete, so it gets deleted. And then we go back up to this node. Well, we've already destroyed its left child and its right child, so then we just call delete on it. And then we go back up to this node, and we try and call its destroy right. So we go to destroy right, and we call its destroy left. And we call its destroy left. There's nothing there, so nothing happens. We go back up to this one, and we call its destroy right. So we go down here to here, And here we try and call the destroy left, but there's nothing there, so nothing happens. Destroy right, nothing happens. Then we call delete. We go back up to this one. It's destroyed its left because there's nothing there. It's destroyed its right, so then we call delete. We go up to this node. This node here, we have called destroy left. We call destroy right. There's nothing there, so nothing happens. And then we call delete. And now this node has had both of its left and right childs destroyed, so we call destroy on it. So you can see here, this is a nice simple case of recursion, and this is why trees are so nice to do with recursion, because we were now able to destroy the entire tree in a very simplistic manner. And there is a bit of a loop going on here in the form of the recursion, but it's a little simpler looking than the linked list loop that we had to write. Obviously, conceptually, it might be a little more difficult because it involves recursion, which may be a little bit difficult to you. But you want to try and get used to this. So again, the destroy here was very, very friendly. So what we can do now is we can go back down to our destructor we've called our destroy, and we are in the clear. What we could do as well is we could now set the root to be null pointer. This will clean up some dangling pointers. It doesn't really cause much of an effect, but it can mean that the memory is a little bit safer. The program is a little less likely to run into problems. I don't know if I would personally do this, but it's fine to do. We can also set the length down to 0 if we want. So it's like the object has been reset, almost as if it was like the result of the move constructor. And remember, actually, looking at our move constructor, that we did everything really in the top. We didn't do anything hardly at all in the function except to edit BT. That's one of the nice things about dealing with an all-pointer solution, where the root is a pointer and the leaves are those little null pointers. We don't need to call insert. We don't need to do anything fancy at all. Okay. So now we want to deal with the assignment equals operator. So there's a really simple way to write these, as I've gone over with a few students before. But you want to say if this is equal to the memory address of BT, then what you wish to do is you wish to return immediately, and you don't wish to do anything at all. So we'll return star this. That said, if you wish to edit the object, we need to go further. So what we'll do is we will call destroy on our own root, which is the result of calling our destructor effectively. And then what we wish to do is we wish to effectively invoke our copy constructor. So our copy constructor said to set the length to 1 and our root to be a new node of root's object. So we'll say our length is 1 and our root is equal to a new node of bt dot root arrow object. So that's what that first line did, right? And then what we want to do is we want to call copy with our root and BT's root. And once that's done, we can return star this. And remember, because copy is recursive, it'll run all the way through. Same way destroy is recursive, it'll run all the way through. So we don't need to worry about calling copy in a loop or anything. The recursion will handle that for us, which is very nice. So anyway, what we can do now is we can go down a bit further and we can take a look at the move assignment operator. A brief bit of refactoring. The reason I paused there was just that, you know, I don't see any reason for copy to have to deal with references. I think it would actually be a little bit more beneficial if it could deal with pointers. So what we'll do is we'll say copy now just takes in 2 pointers. And if we take a look at up here, copy will take in 2 pointers. And we can say here if their node arrow left makes sense now because it is a pointer. Then we want to insert left with our node, which our node is a pointer. It wants a reference, so now we can do a dereference. But it's now their node arrow left arrow object and their node arrow left, as well as our node arrow left. And I think this is a slightly cleaner solution. So anyway, what we can do is we can go up here and we can grab that. And we can go down here and replace the dots with arrows. Okay. So this is looking nicer. We now have our copy function looking a little bit better. And in fact, what we can do is we can actually just say only do all this stuff if their node is true. In other words, not null. Call the insert left on it. And call the insert right on it. Now, if we do have an issue where its children could be missing, so what we can do is we can effectively just move that in. And voila, now the function will immediately stop if their node is null. Which, come to think of it, never happens because we do never call the function in that way. But in the event that we did something dangerous where their node was null, our copy function now would effectively do nothing, which is good to see. So, okay. We now want to write the move, okay? And to write the move, what we can do is we can do the whole link thing again. So we'll say if this is equal to bt, return star this. Otherwise, what we want to do is we want to destroy the root. And we want to set our length is equal to bt.length. And we want to set our root is equal to bt.root. So we want to just directly copy those over by pointer. And then what we wish to do is we wish to set their values to 0 and to null pointer. And in fact, that we've written this code a few times. Now, it's possible that I might not want to keep that. Let's extract that out and call it a function called reset. So we go over here. Reset will be a very, very simple function. There's no recursion or anything. And what reset will do is it will simply take a tree and set its root to null and its length to 0. So if we take a look at our this here, we could simply say bt.reset. We can say reset. And here we can say reset. bt.reset, I'm sorry. Wonderful. So now we have very simplistic, thank you, LEN, very simplistic and friendly move assignment operators as well as our constructors, right? And the idea was, again, that we wanted to try and break the problems down into these very manageable chunks. That's really the art of programming. Okay, so what we want to do now is we want to attempt to insert into the tree. So we'll need to write our search function first before we can do any inserting, because without the search we can't get a node reference. So what we'll do is we'll write our two searches. And again, binary tree : : It does get a little annoying, you might think, to write these out of line, but it's actually for the better. So you might be curious here, node is undefined. That's actually because your search function has the word node written before it, and node is defined within the binary tree. So you'll need to say binary tree : node, which may seem a bit cumbersome, but it's actually for the best. It's being much more specific, because if you have a linked list and you have something called node, it could get in the way. So that's why having it scoped within binary tree is for the better. So node is a full class, but it lives within binary tree. Okay. So what we want to do for search is we want to have a private helper function for search. And the way it works is a little something like this. So what we want to do is we want to say void search, which takes in a, not void, node reference search, which takes in a node, by reference called n, and it takes in the item that you're searching for. So int object. And search will actually not affect the tree. Let's write one that will affect the tree. These functions are going to be recursive, which is why we've created these little private helpers. And I say private, they are protected, which means that any of the children of these trees can use them if they so desire. So whenever we go up here, we'll write those right after our reset. And again, binary tree : in front of the node because it's defined within and in front of the search. Okay. So we can now go about writing our search functions here. And the search function is actually quite simple. If n.object is equal to obj, return n. Otherwise, search through n left and search through the object itself. So, like that. Now, what we want to do actually is we want to convert these search functions, if you'll excuse me, into pointers. And the reason we want to convert them into pointers is it's possible the node won't be there. It'll also mean that we won't have to do a pesky dereference there. Now, whenever we call search here, we do want to return a reference, but we may want to return a pointer just so that we can return the idea of null, meaning the item is not in the list. Okay. You notice there's a lot of pointers with trees. Okay. So now we can call search on simply n arrow left, because this is a pointer now. Speaking of, did we go up there and change them? We did. And if we return a pointer, but otherwise it's about the same. N is a pointer, so we can just return it, and it'd be n arrow object. It would. And compare them. Otherwise, check n's left and check n's right. And if none of them have it, in other words, if we've never returned, then what we can do is we can return null pointer. So what we'll do is we'll actually create a node here. We'll call it node pointer found. Let it equal null pointer initially. And what we can do is we can say found is equal to n. Found is equal to search. Found is equal to search. And we'll only do this, we'll say if not found for each of them. Because it's possible that left could set found. So anyway, we'll put some curly braces and some curly braces. This is an awful way to do curly braces. And then we could simply say return found afterwards, right? Because if found, it was never found, it will return null pointer. But if it's ever found, then we'll simply return. So now what we can do is we can format the document here, and it fixes our curly brace problem. And look at that. Our node pointer found is initially 0. We check its objects, and if they match, we say that found is going to be the n, whatever node we're currently on. Otherwise, we check the left, and we check the right, assuming it wasn't found in the left, and then we return it once it's been found. So this does mean that we're going to have kind of a left-leaning find here, because it'll be the first one that we find traversing the tree, and we traverse the tree starting going down the left branch, and then only checking right branches once the left branches are full. So if the same object exists in both halves of the tree, apologies for moving that, it's going to lie on the left-hand side of the tree here. Okay. So there we go. There's our search function, recursive. And we'll actually copy-paste this function for writing the search over here. This function is only different in that it is not const. Wonderful. So we now have two functions for search. One's const, one's not. And what we can do is we can go down here to our main search, and we can simply say return the result, or sorry, we can say if, get a node pointer, p, or n, is equal to the result of search on root and data. And we can say if, well, we changed these two, didn't we? We did. So now instead of having to store it in n, we can just return the result of this. We could say return n as well, but there's no point in creating the pointer if we're going to return it right away. And the benefit to working with pointers is that in main we can say something like if the search returns, then the data is in the list, and otherwise it's not, right? If it returns null. There's no such thing as a null reference, or at least there's not a well-defined such thing as a null reference, so that's why we aren't doing that. But insert should always work, so we can go about doing this. So let's do that. So what we'll do is we'll create our insert functions next. Though we should probably actually check the code at this point. So before I write the insert function, let's try and compile. And we get some errors. So first off, invalid conversion from const binary tree node pointer to a binary tree node pointer. This is in binary tree on line 48. Okay. So it is not pleased with us dereferencing n and looking at left. That's okay. What we'll do is we'll do it as a, this is going to be a const node pointer. And that should solve the issue. Okay, so on line 102, it says invalid use of Destructor as a type. What it means there is that I messed up the tilde. The tilde needs to move onto the inside. Another issue is that I wrote copy with dereferencing. So I did this on line 115, right? Because now copy works on pointers alone, so we don't need to do anything like that. Wonderful. So we've now done a much better job. We can run make again. And we get just the same number of errors. So invalid comparison of a const binary tree node and a binary tree node. So this is on line 44. So whenever we store this into found, it is not happy. And the idea is that found could theoretically be changeable, which we wouldn't want. So we can try this, but I'm pretty sure that'll be an issue with redefining the pointer. But you never know. Let's give it a shot. Oh, that was fine. Virtual outside the class definitions. That's exactly right. Virtual should only be inside of the header file. And if we scroll up, cool, reset returns, and it shouldn't. Or rather, it is not returning, and it should. So we go to reset here. Right. This is line 126. I apologize. 126, we say BT reset, but you know what we never did? We never did return star this. Wonderful. So we check that. That should be working now, except for the linker errors. Linker errors mean we aren't done writing stuff yet. And they say here, in function copy, we have an undefined reference to insert left and insert right. We haven't written them yet, so we can't use copy. But we fixed all of the big compile errors. And let's continue writing, because so far the code is making sense. If the code isn't making sense, so we're feeling a little afraid about it, what we'll want to do is we'll want to comment out the code that's failing. So we'd want to comment out the copy constructor and the copy function. And we'd want to run the code like that, without those functions. We just want to call search and search for the root and have it return null, or have it return the item that it found, basically. Okay. But now let's try and write insert, because we are feeling good. So to insert left, all we need to do is we need to basically do a check to make sure that n left doesn't have something there already. So the way to save that aside is what we can do is we can say node pointer n left is going to equal n arrow left. Okay. So we save it aside. Then what we can do is we can say, sorry, n dot left, n is a reference. Then what we can do is we can say n.left is going to be equal to a new node constructed from the object. And then we can say n.left arrow. Now we have to decide if we want it to be on the left or on the right. Whenever we do an insert afterwards, should it end up kind of clanking into the left or clanking into the right? Now I'm going to decide to make it clank into the left. But there could be slightly better ways to go about doing this, more intelligent ways, but this is just what we are going to do here. So what we'll do is we'll say n.left arrow left is going to be equal to this n_left that we saved earlier. So this was null, because n was a leaf, and then the new left child of n is going to have null, so it will be a leaf as well. But if it wasn't, then we saved the data that was over there, which is good to see. And then what we can do is we can simply return n.left, that new node that we created, but we have to dereference it because we want to return it by reference, and it is a pointer. Okay. So that was insert left, kind of short and sweet, and we can write insert right now. So this would be n right, which is going to be n right, it's going to be new from the object, and n right, let's again assume we're going to put it on the right, like so. And so the reason that we're kind of doing it that way is the decision that we made there, for those that were a little confused about it, is whenever we take a new node and we insert it in here, this left branch now points to this node, and then this node has two different branches we can go down, and we told it to make the left one connect. Now if we were instead inserting right, so let's say we were going to insert a new node over here, so the right branch goes away, points over here now. This one, we told it we had two branches, left branch and right branch, but the right branch is going to be the one that connects. So the left one is just going to be null, and this is also going to be, back to the blue, null. I'm going to write the null there as a little X, right, just to show there is a branch there, it just doesn't have anything in it. And this way the tree will kind of, if you have stuff that's on the left, it'll extend out to the left. If you have stuff that's on the right, it'll extend out to the right, which means the middle will kind of become a bit of a hollow section. It would be really nice if there was a way we could alternate it. If we could say something like, whenever we're putting it on the left, try and make it so that it will flip to the left or right side, whichever one works a little easier. The benefit of doing things like this, though, is that we're replacing the left node, which means that inserting on the left is guaranteed to be safe. Similarly, we're replacing the right node, so inserting on the right is guaranteed to be pretty safe. So anyway, what we can do now is we can go to main and we can actually start to test some code. So what we'll want to do is we'll want to include Ostream. And remember, you generally want to include your standard library includes. Those are the ones with angle brackets up above your homemade includes, right? So what we want to do is we'll create a binary tree, and we'll fill it with the value 5, okay? And what we'll do is we'll call this BT for binary tree. Remember, you don't need to say equals and then BT. You can just do a nice friendly construct just like that. So BT is now constructed containing the value 5. And what we can do is we can cout bt.search for a 5. Now, of course, for this to work, we'll need to be using standard cout and standard endo. And I'm still getting some errors here. My C++ syntax highlighter is a little bit old, so what you want to do is press Control-Shift-P or Command-Shift-P on Mac, go up here into the C++ configurations UI, and change that to C++ 17 or C++ 20. Voila! So that error has gone away. And what we can do now is we can try and make and run the program, right? So we have an issue, which is that node does not name a type, right? So this is the same issue that we had earlier, where what we want to do is we want to go in here and we want to put our scope here. Okay. So now we print out BT search 5. Let's also search for 4, which is not in the tree. So we would expect that to be null. So the first one we expect to be a memory address, because memory addresses print out. The second one we expect to be 0. Right, so we can try and run the program now. So we'll /me. And we can see here that we get to 0, but then we have a segmentation fault. So that's not good. So that means there's probably an issue with our search. So let's take a look. We search the root and the data. And we go up to our search function, and our search function says if the object is found, if the object is not found and n left exists, similarly, if the object's not found still and n right exists, because otherwise we're just going to go read some null pointers, right? So what we can do is we can run make, we can run it again, still get a segmentation fault. So maybe if n exists. Alright, so now we need to make GDB because we clearly aren't figuring this out on our own. So we can run, and we can type BT for backtrace. And we can see here that this is the pointer, and n is the other pointer, and the object is 3 that we're searching for. And it called search where n was null. So why did it call search where n was null? First off, let's double check our makefile. So the makefile here defines a ton of variables, and at the top, binarytree.cc is one of the input headers, which means that every time we change it, it should result in us recompiling the program. Is that something that we saw happen? Whenever I would run make, yes, the program appears to have been recompiled. And it was if n arrow object is equal to object. But we have now fixed that. So if we quit out and we run make run, let's say something to the effect of n is explicitly not null pointer, because that counts as a change. And now we can run make run to see if it is updating it. It is compiling again, but we're still getting the same error. So if n exists, if not found, and n, and so basically we can't do anything if n doesn't exist. So what we'll do is we'll just say if n exists, then we can actually check stuff, but otherwise we can't do a darn thing. Because what we were doing here was we were saying n arrow right, but n didn't exist. So we could add an n to every single one of these, but that's a bit of a pain. So we'll do this. And then what we can do is we can now make run. Oh, come on. Make GDB then. Let's see what's up. Run the program for me, please. And it's on line 62 that it's talking about n arrow object is equal to object. Binarytree.cc line 62. There's no line 62, so there is. See, there's two different search functions. Oh well. And obviously this node doesn't need to be const now. That is the issue with duplicating code. But wonderful, we now see the 0 that we were expecting. So our search function seems to work. So now what we can do is we can actually save the root. So we can say auto root is equal to the dereferenced bt.search for 5. And we now have the root saved, which is a binary tree node. And then what we could do is we can use the root to be able to insert to the left and to the right of things. So we'll make it a reference, by the way, to the node. And what we can do now is we can say bt.insert left of the root, and we'll insert the number 3, and .insert right, and we'll insert the number, 10. So, right, we have to tell it to the root. because we want to insert to the left and to the right of the root. Excellent. So now what we can do is we can print out these, so we can call it auto reference root left, and similarly root right. So now what we can do is we can print out the memory address of the root, which is what we could find with the search. We can print out the memory address of the root left, and we could print out the memory address of the root right. Okay, so if we run that, we can see here the root left, and the root right. And they are different memory addresses, all of them, which is good to see. And what we can do actually is we can now do some automated testing. So we can say if root left address is not equal to the result of bt.search for 3, cout error left child not found, end of line, and we can add an else and say found left child. And the same thing with root right. We can even do the same thing with root itself. So we could say if root is not equal to bt search 5, error root is not found. And we'll change this to say right. Oh, apologies. Okay. So we run this, we can see that we found the root, found the left child, and found the right child, which is good to see. So that means our insert is probably working. Right, we can write some more inserts if we were so willing. Like, for instance, we could say, you know, now that we've done all this, we can say bt.insert left of root left, and we want to insert a 1. We could say insert right of root left. We want to insert, say, a 4. And then we say insert left of root right, and we want to insert 7, and insert right of root right, where we want to insert a 17. Okay, and this should just work. Seems to. So now we can also do some print statements. We can cout bt.search for a 1, and it should be in the tree now. And search for a 4, and search for a 7, and search for a 17. Right? And tell you what we'll do. We will not write these all as separate cout statements. We could just do that. Wonderful. And if I format the document, they look a little nicer. We can make run. Boom. So the memory addresses came out. So they did make it into the tree. At least they are findable. Now, this tests that we can insert new leaves, right? Because we're inserting at the very bottom of the tree. Let's see if we can insert within the tree. So what we can do is we can do bt.insert right from the root. So it should move the right children down. And we'll insert the number 6. And now what we want to do is we want to do a search for that number 6, see if it's still there. And let's also repeat searches for the numbers 7 and 17 to make sure that they're still there. And their memory addresses shouldn't change. So if we run make run, we can see here that we were printing 1, 4, and then we were printing 7, 17. So that's 6, 8. We put in the 6, so that's A, and then we go back to seeing 6, 8, which are going to be still within the tree. So that's good to see. So that means that our insert seems to be working nicely. And what we can do now is we can try and write the print, because it's kind of hard to get a sense for what the tree looks like with doing these little tests here. So what we'll do is we'll write a print. And I'm skipping remove for right now, because remove can be a little more complicated, but there we go. So what we'll do for our print is we will say the following, which is that the print is going to call a print function that we have, which is going to be a recursive helper, a lot like the other recursive helpers that we've done so far. And this function is going to be void, called a print, and it will take in an Ostream called OS by reference. It will take in a node pointer called n, and it will do also a level, which is going to initially be 0. So I've written in default 0 there. So now what we can do is we can simply, in our operator stream, call print with os and bt.root. Now, we actually need this to be a const pointer, or that's going to fail. And it should be a const function in general, so that it is callable. We need to say bt.print on os and bt root. I'm not sure that that's correct. I think that we need to do some checking here. Sorry, Ostream reference like that. Was that the issue? It was largely the issue. So we haven't got a return statement. That's correct. So what we want to do is we want to return OS as soon as print is done. And now we can write print. So if we refresh, print is not defined, which is good. We can now write it. So we'll go back here to the helper function section. And what we can do now is we can write the print function. So in order to do this, we'll need to put the scopes. And what we want to do is we want to first print out a number of spaces based on the level. So what we'll do here is we'll call this char spaces and let it equal 4 spaces. I find that this is nice. It gives you a lot of room, and it's a little bit more flexible than a tab, because tabs can suddenly start to look all misaligned whenever we do this special kind of print, because we're actually going to be printing the tree upside down. Or not upside down, but sideways. Okay, so we're going to do this print what is called an in-order traversal. And we're actually going to do a reverse in-order traversal. The reason is that whenever we tilt the tree sideways, so I want you to imagine that this is our tree and we want to print it out, it's going to be rotated sideways. So I wish there was a rotate tool in here. But the idea is it's going to come out something like this. Right, where this is the same tree, but it's just sideways, right? Here's the root. And the reason we do this is that it's really easy to write recursively, and it has a really small stack depth. So the stack, which is how many recursive calls that you end up making, each recursive call adds to what's called the stack. You want to try and minimize that, particularly on lower powered machines. It's not something we have to worry too much about today as programmers. But even as early as like 1990, and early 2000s, you wanted to care about reducing the amount of stack space. So, you know, we haven't had to worry about it for 20 years, but that's not very long in the grand scheme of things. So try and be good to the stack in general. Okay. So what we want to do now is we want to call the print function, though we need to only do stuff if the node exists. I forgot to mention that. So if the node exists, is the only time we want to do anything. This is going to be fine. I think we can just do that, and I'm pretty sure that'll be okay. Const expr is a bit of a stronger form of const, but it means the compiler can do a bit more. Sometimes you can't apply it to things. I'm pretty sure in this case we can. Wonderful. So now n, if it exists, what we want to do is we wish to call print with the same Ostream, but now we want to call it on n's right child. Again, we're going to go a bit in reverse order, which is why we started n's right child. And we want to increase the level. So we'll say level +1. Okay? And then what we want to do is we want to actually handle the in order part. So in order means between the two recursive calls. So the first one, if we did something above here, this would be the pre-order part, which is going to be unused in this case. Then we do the first recursive call, then we do the in order part. Then we're going to do another recursive call at the end, which would be the post order part. So this would be the, again, we do n arrow left, and we're going to again say level +1, right? Because level is kind of the depth. And then the final action happens down here, which is called post order. Our destructor is post order. But we want to write the in order section here. So the in order section, what you've got to do, which is also unused, by the way, if it doesn't algorithm, is we want to print out a number of spaces equaling the level, and then print the node and go to the next line. Okay? So what we want to do is kind of if, or not if, for size t int I equals 0, I is less than the level. Increase I. We shouldn't expect it to be very large, so we don't really need size t, and we called level at int up here anyway, which is probably a bad design decision, but what can you do? And what we wish to do is we wish to send into the Ostream spaces, just kind of repeatedly. And then once that's been done, we wish to send into the Ostream n's object itself, followed by an end of line character. We don't need to do a full ENDL, that'll actually slow the program down. So let's try and avoid that. And what this will do is this will go through all of the prints for us, and they'll all print out their node and go to the next line. So this print function, this recursive print function, is very kind in that it will print everything out on its own fancy line, and it'll be kind of rotated to the side a bit. So if you don't believe me, we can now try and print BT and take a look at what it looks like. So what we can do is we can say cout BT and del. Right? So we can run make run, and you can see here that it ain't working. So whenever you write code, you put default arguments in the header file. You're not supposed to put them in the CPP file. Something was off. But we make run. It compiles and runs, and look at that. Remember we did initially, if we look back at main, we put 5 as the root, so 5 is the root. And then we inserted a 3 to the left of 5. So you tilt your head a bit to the side, you can see the 3 is to the left of 5. If I draw the line down the middle, to the left of 5 is the 3. And then, to the right of 5 is a 10. Although not quite, because we ended up putting a 6 in there later. But then we inserted a 1 to the left of the 3, and we inserted a 4 to its right, that worked. Inserted a 7 to the left of the 10, and a 17 to its right, that worked. We inserted a 6 to the right of the 5, and that's what we can see. And remember what we talked about, how it would shift the children down? That seems to be what happened. So tell you what, let's comment out this line. You can see that this whole subtree, 10, 7, 17, with this one line in, is shifted downwards by the 6. The 6 shifts it down and to the right. Even the furthest left element in this subtree is to the right of the 6. Okay. So that is kind of the basics of the binary tree that we have here for the most part. Let's try and handle remove. Okay. So remove. All right, we haven't copied it over yet, so let's do that. Removes will go in here. We've got 3 of them, right? So what we'll do is we'll paste that in. Okay. And every single one of these is scoped into binary tree, so we'll do that. Not a problem at all. Okay, wonderful. And they have all been scoped into binary tree, and what we want to do now is we want to kind of handle their remove. So the way to go about removing whenever we have an object is we want to be able to find the node that has the object as its child, because we basically want to have the parent. So what we can do is we can go out and we can write a find function, which is very similar to our search. And what we'll do is we'll write it over here. We'll call it find with child, which takes an n and the object. This is a bad name, by the way, find with child. You can come up with something much better, I'm sure, without even trying. But it will get the job done. So find with child, what it's going to do is it's going to search through all the nodes until it finds one whose child is object. So what we'll do is we'll say if n, if n arrow left, if n arrow left arrow object is equal to object, return n. If n arrow right, if n arrow right arrow object is equal to object, return n. Else, return null pointer. And then if it doesn't have it, then what we could do is we can simply call find with child on n arrow left. Whoops. Find with child on n arrow right. Okay. And this will go through them. Now we still have to pass it the object. I'm terribly sorry. Wonderful. So now we've gone through, we found a node that has a child called object. So we go back down here to our remove. What we can do is we can say node pointer n is equal to find with child, starting at the root, going down to the object. Notice you mostly start at the root whenever you do these kinds of things. And so now n is going to be the node with that node as its child. And then what we can do is we can say the following. So that node that is its child has at most 2 children, and we want to bring one of them up. So what we can do is we can say if n exists, if n has a left child, we will bring up that child to take the place of n, and we will need to try and attach its right child somewhere. So you can see the remove is a little more complicated. It's probably best to try and draw out. So if we have a node, let's say you have a simple tree here. Okay. And we want to remove this node. So what happens? Well, either this node can jump up and fill the spot, or this node can jump up and fill the spot. And if this node has children, or this node has children, what do we do with them? So if this node jumps up to fill the spot of the missing node there, we'll need to jump up its child too. So you can see the remove is basically going to have to be something in the order of logarithmic, because we're going to need to pull up the children. Okay, so what we'll do is we'll say if the n has a left child, then the left child is something that we can move up. So then what we'll do is we will say n arrow left. Sorry, we have to determine which one has the data. So we say if n has a left child and n's left child contains the object, then that's the one we're removing. If n has a right child and n's right child contains the object, then that's the one we're removing. And that actually makes our life easier, because we can actually call the remove left and remove right functions that we've already written. We can remove left of n with the... That's it, actually. And we can remove right of n. Okay, good. And of course it's called object, not obj. And we don't have to return anything. This function's void. So this will just call the remove right or the remove left and, you know, do its work as necessary. So again, the reason we check first if n has a left child, then we check to see if its left child is the one to remove. Similarly, we check if it has a right child, and we check to see if it's the one to remove. Turns out we could remove both children by doing this. But we will only remove children of a singular node, because find with child returns a singular node. So, bit of a caveat there. It doesn't remove all nodes that have the object, but it could return two. So this is probably not a very well written or well defined function. But the idea is to try and keep things a little bit simpler. What we could do actually is we could say do this while n exists. This will say basically find all of the nodes that contain the object or have their children contain the object and remove the children that contain it. So this really removes them all, but it's not a very efficient solution. It's just something that we were logically able to put together easily. Okay, so what we can do now is we can write remove left. So remove left says we now know the node that we're going to remove exactly, which is this one. We're calling remove left on the root. How do we deal with that? So this is the problem we were talking about before, trying to shift them up. And again, we're just going to have to kind of go down the way and pick them up. But since we're removing the left node, we know that we can try and pick up there from the left side. If we don't have anything on the left side, we'll have to pick up from the right side. So what we'll do is we will say we're removing the left from n. So what we can do is we can say if n dot left exists, which it almost certainly should, then what we can do is we can say n dot left is going to be equal to n dot left arrow left. Now we only want to do this if n dot left arrow left exists. I'm terribly sorry, because if n dot left arrow left exists, then this will work well. Tell you what though, we do want to have actually a whole if n dot left. because, you know, it's possible that we called this function on something that didn't have a left child. So we want to set n.left to be n.left arrow left, and we want to then remove left, whoops, of n.left. So what on earth is that doing? Well, it is going to go and let, apologies, it is going to go and let this node move upwards. So let's give them labels. So this will be A, B, C, D, E, F, G, H, and I. Okay? So if we want to remove B, what this will do is this will cross out the B and replace it with a D. Okay? Because we've copied that up. But then what we do is we call remove on the D, because it doesn't need to be there anymore, because it has been moved up. So we will call remove on the D, which will then replace it with the F. And then we'll call remove on the F, which will replace it with null. So if n dot left arrow right, then what we can do is we can say n dot left is equal to n dot left arrow right. We only want to do this, though, if the left child doesn't exist. And then what we wish to do is, should we call remove left or remove right on the right child? So if we call remove left on the right child, then the H would vanish and go back up. So that would mean our tree would always kind of lean a little bit. I'm more in favor of calling remove right. So what we'll do is we'll call remove right on n.left like that. So that'll go clean up in much the same way. Now, if this isn't the case, what we can do is we can simply say delete n.left, n.left is equal to null pointer. And as a result, the size has gone down. So what we can do is we can say minus minus len. That's another thing we weren't doing, is whenever we were calling our inserts, we weren't increasing the size, which is something we probably should do. So what we'll do is we will say plus plus len. Wonderful. So now the tree can grow and shrink in terms of its size. So anyway, we've now got our remove left that will work a little nicer. And we can now go about doing a remove right. So, by the way, if it turns out that n.left doesn't exist for whatever reason, then this function will not do anything. It will not decrement the size, it will not delete, it will not assign to null pointer, which is good. Let's copy this, and we'll use similar logic for remove right. So if n.right exists, if n.right arrow right, then n.right is the right, remove right of n.right. But if n.right arrow left exists, and the right didn't, then we can say n.right right left is going to be n.right, but we want to remove left of it. So in other words, if the child's missing on one side, pick up the child from the other side, and then try and continue down that chain until you run out of children. We want to delete n.right is null, and decrease the length. Okay, good. And this only works, again, if the child exists. Otherwise, nothing happens, right? One thing that we will want to do is we will want to return, before we delete, we will want to save the data aside. So what we can do is we can save the initial data aside from the very first call, because that's the one that we want to return, because that's the one that the user cares about. So what we can do is we can say int data is equal to n.left arrow object. And then what we can do is at the bottom here, we can just return data. Of course, here it'd be n.right arrow object. We'll return the data. And in the case where it doesn't work and we can't return anything because there's nothing there, what we can do is we could return a value like endpost. So let's actually define one of those. So under the public section, simply define a static const expr size type called endpost, and let that equal -1. And since it is a size type, it'll be an unsigned value, so we get this nice huge integer. That's our endpost. So what we can do is we can just return endpost. Right, it wasn't there. So this isn't a great approach, but it should be okay. And endpost being constricted into an int is not ideal either. So what we should probably do is we should actually probably just return 0 or some other value, because that is an int. Endpost could be useful though later on, so I guess we can, I'll delete it. We don't need it, right? Okay, cool. So that's better to see. Now whenever we template this, we'll need to change some things up, but this is a nice non-templated binary tree. Let's actually ensure that things seem to work. So let's, after we print out the tree, we'll print out bt.size. Which is 8. And does that make sense? 1, 2, 3, 4, 5, 6, 7, 8. Again, that's 1, 2, 3, 4, 5, 6, 7, 8. So yes, the tree has 8 elements, which the size is correct, and we'll try and remove some now. So we'll do bt.remove of, you can't remove the root. So removing the root with the remove function that we wrote will not work because there are no children that contain the root. So we'll actually need to add a special case to our remove if you're trying to remove the root. And if you're trying to remove the root, glad we thought about this. It was almost something that I missed entirely. If we want to remove something that has the object and it's in the root, what we can do is we can say if the root exists and if the root object is equal to object, then what we could do is we could let the following things happen. If the root left exists, then we can say root object is equal to root left object. Actually, come to think of it, what we could do is we could, if the root left exists, we could save a node pointer and call it del for delete, and let that equal the root. And then we can say that the new root is going to be, well, no, we can't do this. So I was trying to get clever, but we have the same issue as before, or what happens if we have both children. So what we need to do is we need to basically pick one of the two children, and this is if the left child exists. What we want to do is we want to go about doing a lot of what we did here. So what we'll do is we'll say root is, the root's a special case. So let's go and draw this. So, whoops. So if the root is here, and we want to try and remove the root, let's say we have two children. we could let one child come up and fill it, but let's say those children have children too, so we just can't directly take it. What we could do is we could let the left child fill it if it exists, and then remove the left child. We could let the right child fill it if it exists, and then remove the right child. Okay, so if the root exists and the root has a left child, we can let root object equal the root's left child's object, and then we can remove left of the root. Right, it has to be the referenced version of the root, and it should actually be root arrow left if we think about it, because we want to remove the left child of the root, and that's because we've already copied it up there, so that'll take its children and put them up as necessary. And remove left and remove right will decrement the size for us as necessary. But we'll say an else to this. Else, if the root right, then take the object from the root right and call remove right instead. And then else, if neither of these work, what we can do is we can actually just set the root to be, we have to call delete on the root. And we can set the root to be null pointer and the size to be 0. So we can reset. We don't need to decrement the size because the root being the only element, because it has no left children and no right children, means that its size is 1 by definition. So we can simply reset to make its size go down to 0. Very, very nice. And wonderful. Yeah, okay. I'm feeling much better about this code. So we try and remove the 5. Let's try and print the tree and that after having removed 5. Okay. Statement has no effect. Line 196. Right. Meant to do that as a single equal sign. That's my bad entirely. It should actually be if root object is equal to the object that we're trying to remove, then we wish to do this. Nice. Okay. So if we take a look, the original tree is still there at size 8. We tried to remove the root, and the size went down to 7. We did not end up getting the behavior that we wanted, where the subtree, the 1 and the 4, should have moved up. It should have flipped the 1 up, so it should be 3, 1, and the 4 still on the right. So let's take a look at our remove left and see what happened. So whenever I called remove left on n, which was the root, that was the 5, what we did is the following. We grabbed the data, which was in n left's object, and if it had a left child, we moved it up and we called remove left on n left. Can we move it up in this direct way? I don't think so. N left's object is going to be n left's object. Now we can remove left, and n left's object is going to be n left's right's object. I think this is a slightly safer approach. And then we don't need to call delete every single time. We really only want to call delete the one time, the very last remove. So what we can do is we can just say else, if it doesn't have any children, that's when you'll delete it and set things to null pointer. And decrease the length and return the data. Okay, that's looking better. So let's do a similar thing over here where we'll say else. This code come on up. Okay, and that's a little better, and we want to do the same thing here where we say the objects need to become equivalent. Because really that's what we want to try and move around. I don't like to reassign pointers if I don't have to. Okay, make run. Nice, and this is the subtree that we expected now, where 3 had 1 as its left subtree, which had 4 as its right subtree. And we shouldn't be getting any memory leaks. Let's make sanitizer to run it through the memory sanitizer. And it looks like we didn't get any memory leaks because it didn't complain. We'll make valgrind just to be safe. No leaks are possible. So it looks like we've written a very nice memory safe binary tree, which has the ability to print and insert and remove. So this has been a really long video already. It's basically 2 hours. So what we can do now is we can talk about templating it. I'm going to add some timestamps to this YouTube video. Of course, you see them already because you're watching the video on YouTube. And you should be able to skip around. So if you're only interested in the templated part, then, you know, welcome. It's a pleasure to see you. But okay, so we want to try and template this now. So what we can do is we can say template type name t. And now instead of being an int object, it'll be a t object. Instead of being an int object assigned 0, we'll do the default constructor for t. And instead, excuse me, of things like search, which take in an int, they'll take in a const t reference. So the reason we want to do a reference is that passing a whole t object around is expensive. We want to try and avoid doing that whenever we can. Okay, level though is still an int because it is the depth of the tree. And I do actually want to change that now that we're talking about it. Okay. Might as well. Okay, so back to here. We can do another const t reference. The root object can now be a const t reference, and these should all, of course, be binary trees of type t. Okay. They should return binary trees of type t. Okay. And search can still return nodes, but they now take in a const t reference called data. And insert left and insert right will insert a const t reference, and remove will return a const t reference. Okay. Not a const t reference. It'll actually have to return a straight up t value because it will not exist in the tree anymore. That's kind of the point of remove. Okay. And then this will be a binary tree of type t here. Okay. And we can go back over to the fact that it's a friend, and we need to say that it's a template of type name it for inner t. And we'll just have to change this to say it, like that. Which is just a silly thing about the way that template friend functions work. But anyway, we fixed that. So now what we want to do to template this, we go back up here to our copy function. And it's now going to work on a binary tree of type t like this. So what we'll do is we'll copy this, we'll go to Control F, and we'll say all the ones that aren't like this. Whoa. We need to undo that. We want to replace them with binary trees that are like this. And in fact, whoops. What we want to do is we want to go in here and we want to write template type name t, because that'll fill us in. Okay. And if we Control Alt Enter to replace them all, Now all of our functions have a template header, which is really good to see. Though the types have all been messed up, so we'll need to go and fix those. So there we go. Perhaps inserting the template header all at once like that was a bad idea. Okay. That's just wrong. Like that. It's fine. Right, but instead of an int object, it should take a const t reference, like that. Wonderful. Okay, so let's discuss some of what we just tweaked a little bit with this function. So we had to put in the template there, but it accidentally put in 2 templates. We had to go and fix it. And if I format document. The real issue that we had was that it was an int. We had to change it to a const t. The interesting thing about Node, you notice Node isn't really templated just because the template's inherited from its... not inherited so much as like brought in by the... not base class, but this is a outer namespace, outer scope. So, okay. We'll delete the extras, kind of like what we did before. And again, this is going to be a const t reference object because just because the function isn't const, the object shouldn't have to not be const. That was a bit of a weird way to say that. But there we go. Okay. These ones are always pain to fix. There we go. Gosh, I love the simple ones. Okay. So this constructs a binary tree. It's constructing the length as being 1. That's fair. And it's constructing a new node with the int root object. That's because it should be a const t called root object. So that's an issue I've been putting into all of these, haven't I? Okay. Binary tree of type T, which is always good to try and state that whenever you possibly can. Okay, just return a binary tree of type T by reference, but the template goes there. Cool. And again, it'll return a binary tree of type T by reference. Whoops. This is probably something that we want to have in quotes, even though it's a simple one-liner, or in curly braces. Okay. And again, const comes down, and that goes away like that. And we want data to work on a const t reference. So I'll just pull that out of the wazoo. Again, delete this. You can see here the converting to a template is a very tedious process. Not a lot of fun, but gotta be done. So, okay. All right, and gotta replace that one. This returns a void. And remove returns that. Or not returns, but takes that in. This is an int. This is an int, but it's not. And it's not. So now we're returning nothing, but we're still doing comparisons, which is good. Right, so this is now a const t reference called data, and we'll return data, and otherwise we'll return the default constructor for a t object. Especially because it's not returning a const t reference, it's returning t itself. T called data. Data is not a const t reference up here. It should actually just straight up be a t that we extract. And otherwise we will return the default t constructor. And this is actually going to be a binary tree of type t. Okay, format document. Okay. Right, we'll need the template line here as well. Wonderful. Okay, so now we have a template of our binary tree, I think. Let's try it. Okay. So you need to add type name in binary tree.cc line 43. Right. So this is a bit funny, but since this isn't actually a type, we need to write it within like that. So what we'll do is we'll copy this, and then I'll undo that change, select this, and we'll click find, and then we will Control H, and I'll click paste, and we can do Control Alt Enter, and they all get replaced. So now what we can do is we can write make run, and cool, the program ran just fine on our ints. So whenever I said binary tree here, it just interpreted the type as being a 5 because the constructor required a type t. But let's actually write that manually. Wonderful. So now what we can do is we can include string, and we can create a binary tree of strings as well. So we'll do this is we'll create a binary tree of strings, and we'll let the root be sentence, and then what we can do is we can say auto reference word, or auto reference sentence is going to equal bt dot search for the sentence. So there should only be a few public search functions, and they should take in const t's. So I think that this is wrong, that it's just not seeing it. Let's take a look. Conflicting declaration. C++ 11 extra string. Right, that's fair. BT sentence. Okay. Right, so this is an issue where whenever we construct, sometimes we want to insert a full object. So the way that we can do that is we can do it as a full t object. The const will make our lives more efficient sometimes, but sometimes for const L values like this, can't do that. So okay, and then we'll also need to do this probably for our insert functions. Oh, I'm terribly sorry. The constructor was fine. Yeah, constructor is fine. It was the search that was a problem. the search was trying to run on the non-const version of it because I let this be a non-const. So if we look at the search function here, this one should be able to take in a full t-object of type data. Because it wasn't able to bind a non-const L value reference of the node pointer to an R value of the node pointer. Sorry, what? Main.cpp line 59, it was this search that was freaking out. And it was saying the reason was that it was calling this version of search, which if I go look at this version of search, it's right here. Okay, so sorry I was very quiet there for a bit. I was doing some kind of in my head working out what might be going on here. And I think an easy solution might be for us whoa, I copied insert. For us, for our search, to just have one of these that is a full object. This can just make the compiler happy. Doesn't make any sense to make that const. Doesn't need to be. Excellent. So if we run this now, okay, it'll be that it's ambiguous, or I think I grabbed search from the wrong place. This is why my names aren't very good. You probably want to pick better names than I did, because the search that I intended to use was here. Now what I fear is that it won't be able to choose between them. So the reason I fear that it won't be able to choose between them is that the way C++ tries to determine type is it tries to find whatever one will fit best, and these two both fit equally well, a full object or a reference, right? So that could be a problem, but let's hope that it isn't. Okay, cool. So now what we can do is we can try and run this, and we should just get a ton of errors because they're all ambiguous. Call to overloaded is ambiguous. So now what we can try and do is we'll try and remove the search like that. And remove the search like that. And let's see if this solves the issue. Cannot bind a non-const L value reference of type node pointer by reference to an R value of type node pointer. Maybe this needs to be const. Let me just double check the struct that I wrote. Yeah, it is a full T that's there. Okay. I much prefer my old search to this new search, so what we'll do is we'll just comment them out. Right, I'll need to go into the CC file and comment out those searches. Okay, please compile. It did. And it ran. We got a warning, unused variable, but the string is running now. So the fact that this is written as a C string, I think, is what required us, because it's a const char, what required us to use const here. That's the only reason. Anyway, we can say sentence, and then what we can do is we can say, in fact, did I do that before? I dereferenced it before. If I do that, do I need the word const anymore? I don't. That's good. Okay, so that's all I was forgetting. Wow, it's just a pointer to a reference conversion. That was blindingly obvious. Haha, sorry. Okay. So what we want to do now, though, is we want to say bt sentence dot insert left of sentence, and what we want to do is we want to insert the subject, and then we'll insert to the right, and we'll insert the predicate. And what we can do is we can insert to the left. Well, we can print out now the BT sentence. It's fine with me. Like that. So if we take a look, we get the sentence and the subject and the predicate. So a sentence is made up of subjects and predicates. So that is the binary tree in a nutshell, templated version and all. Oh my gosh, we ran 2 hours and 20 minutes. So sorry that took so long. That's honestly a movie, but hopefully you didn't watch the whole thing. You just went through the timestamps. But this is a binary tree, start to finish, no notes, no references, and a lot of debugging in the middle. But we've now got a fully templated binary tree split among multiple files that we can use. We have a makefile for it as well. And in future, we can talk about extending this binary tree into a binary search tree and into a binary heap. Wow. Okay. Thanks, everybody. Good night, and, stay safe.